right, hello everybody, and welcome to our continued discussion on sequences. First, we are almost at the end. We have one more chapter, chapter 3, that's in the same uh, vein as the previous one, and then fourth chapter that is worth knowing but will have a different format. Uh, all right, so let's look, excuse me, let's look at what we've done so far is, ooh, writing looks weird. Arithmetic sequences, sequences, where, for example, we have 1, 7, 10, 15, and so on, where as long as we add the same number every time, it doesn't matter what that number is, we could subtract. We classified this as an arithmetic sequence, and we derived what the formulas look like in general, and then we use those formulas in a couple of different kinds of questions to get used to this. Then we also built on top of this type of sequence fancier, more general sequences where the numbers I add every time are not the same, and we call them generalized arithmetic sequences. They are connected to the arithmetic sequence, but for deeper down somewhere. And we saw by way of the triangular numbers that even that direction of generalization leads to definitely more complexity. So it's good to look and then pull back when we realize, okay, it's a little bit too complicated for us. Good to know it's there, but we're happy where we are. We could go in a different direction, but by realizing that I don't have to add or subtract, I could multiply or divide from one term to the next. So let's look at an exercise to help us introduce this idea. Exercise 3.1. The number of fruit flies doubles every day for 10 days. Day 1, I have 10 fruit flies. How many fruit flies will be in the jar, and what does the sequence look like? So I start with 10, and it doubles every time. So exercise 3.1, see what is the sequence that we get. So day 1, I have 10. Day 2, I'm going to double that to 20. 3, I'm going to double that to 40. Day 4, I'm going to double that to 80, and so on. So now it's different. It's not an arithmetic sequence. I'm not adding by the same amount. I'm multiplying. But the pattern is still very, or fairly, I hope, easy to recognize. And that means if I can explain it in words, I can write a recursive formula, which is just a direct translation of those words. Start at the first term, which is 10 in this case. And then I have to just translate the fact that if I want the term, I take the previous one and I multiply by 2. And that is how I'm going to get terms in position 2, 3, 4, so on. So It's not hard to explain in words what we do here. It's just a generalization in a different direction. Instead of adding, I now multiply, and that sets me off on a different path, different kinds of sequence. Now, I've never seen this kind of sequence necessarily in this light before. It does look very similar to the powers of 2, but it won't always. It's because I start with a nice 1 here and I have a nice 2 multiplier. So I don't want to rely on that. In order for me to try and examine what the explicit formula could look like, it helps me to make a little table, try and find a link between the position and the term in that position. First 5 should be sufficient. So, first term, I have a 10, then I have a 20, then a 80, the next one would be 160. So let's pull these numbers apart and see how they can be related, or how their calculation can be related to the position value only. That's what we do on a basic level to find an explicit formula. So 20 is the previous term 10 times 2. 40 is the previous term times 2. But that 20 has an expanded version of 10 times 2, and then I multiply by another 2. 80 is the previous term times 2. That's what our recursive formula and our observation said. That 40 has an expansion of 10 times 2 times 2, and then I multiply by another 2. Or 160 is 80 times 2. 80 itself is 10 times 2 times 2 times 2, and I multiply by another 2. So if I just sort of line these up better, see here backwards, 160 was 10 times 2 to the power of 4, repeated multiplication. 10 times 2 to the power of 3, 10 times 2 to the power of 2, 10 times 2 to the power of 1, and technically the first term still fits that as 10 times 2 to the power of 0, because 2 to the power of 0 is 1. So I just get my 10. So now I see there's a lot of consistency here from one calculation to the next. The 10 is always the same, the 2 is always the same. It's just the powers of 2 that change. So if I now extend that to a general position n, it's always going to be a 10 in this example. It's going to be a 2 to the power of, well, power of 2 that I have in the calculation is always 1 less than the position I'm in. So if I'm in position n, the power is n minus 1. And there is my explicit formula. For this example, yes. Let's write it over here. So we have our explicit formula as a n is what I want to find. 10 times 2. And that'll get me the terms in position 1, 2, 3, and however far I may want to go. So now I don't want to be too connected to this specific sequence, but rather notice the places where the key properties of this sequence, where they go in the formulas. I have the first term and I have the number I need to multiply by. Just like in the recursive formula, once I know those two things, I can set up the whole sequence. Those two things, the parameters of the sequence, need to feature in my explicit formula as well, and they do. 10 and 2. So now I'm going to just state this in general without the 10 and the 2, but any first term and any number I multiply by. So in general, our sequence is going to start with some first term a, and then I'm going to multiply by some number r to get a times r, and then I'm going to multiply by the same, whoops, not 2, r. So then I have a times r squared, multiply by r again. A feature of the sequence is I multiply by the same number every time. So this is called geometric sequence, first term a, and we call the number I multiply every time the ratio r. I can extend my formulas by looking at my specific example. So formula is really just the direct translation, right? Start with the first term, and then to get the general term, take the previous one and multiply it by the ratio. Just putting in an a and an r in the appropriate places. Take the first term, and multiply the ratio to the power of n minus 1. So now, just like in the case of the arithmetic sequence, the whole point was that if I can identify a sequence as an arithmetic sequence, I can immediately use the formulas specified to that example. Of course, it'll have its own first term and so on. But I know everything about it because I know the formulas and I can answer any question. Same thing is going to happen here. If I can identify the sequence as a geometric sequence, then I know everything already. I know what they look like, so I can explain them. I can jump around in the sequence. I can do whatever you want me to do. But it's a different kind of sequence with different formulas because I wasn't doing the same thing. I wasn't adding, but now I am. So we have a simple example just to get us warmed up. This new kind of sequence. By way of example, or exercise rather, 3.2, where we're given a formula sequence. I have to decide, is it a geometric sequence? And if it is, what is the other kind of formula? Explicit or recursive, the other one that they don't give me. So, exercise 2. So we're doing very much the same kind of questions, just for this new sequence. My formula that they give me is 2 times n squared. N is 1, 2, 3. Let's get the sequence for at least the first 4 or 5 and see if it satisfies the requirements of being a geometric sequence. Well, the first term, n is 1. 1 squared times 2 is 2. Second position, n is 2. 2 squared is 4 times 2 is 8. Next position, 3 squared is 9 times 2 is 18. Next position, 4 squared is 16 times 2 is 32. I can keep going, but I already see the jumps from one to the next not the same. I would have to multiply by 4 to get from 2 to 8, and that doesn't work. Next one. So it is not a geometric sequence, and I stop that. Do I multiply by the same number every time? No. If it's a no, it's some other sequence that I don't have much knowledge about. Perhaps. because our knowledge is fairly limited, we can't do much with just any kind of sequence. Here's another formula. Now I remember my explicit formula for the geometric sequence in this way. Just like for the arithmetic sequence, you could simplify it, you could do many things. I didn't care. I memorize it in one way, a way where I can see the pieces very nicely. That's my choice. And I'm going to take that same choice here. This is how I memorize it. This is how I'll use it. Anything else? And I don't know. It kind of looks like it, but I'm not sure because it doesn't fit the way I memorized it. And that's okay. All I need to do to be sure is find the first few terms of the sequence. That's not a problem. First term, 2 to the power of 1 times 4 is 8. Next term in the sequence, 2 to the power of 2 is 4 times 4 is 16. Now we use nice and easy numbers, so these might look familiar, but I could have used other numbers, of course, as well, right? It just makes the calculations a little bit more difficult to do in my head. Power of 3 is 8. 8 times 4, 32. Power of 4 is 16. 16 times 4, 64. Now don't think that, oh, I see that one of the 4 basic sequences here, so I can just use that. It's only because my numbers are easy for quick mental arithmetic. It doesn't have to be a 2 there, and the sequence would look very different. But I do see that I'm multiplying by 2 in this case every time. This is a geometric sequence. Sequence with first term 8 and ratio 2. They tried to simplify the formula. They tried to mask the key things about this sequence. The first term is 8, the ratio is 2. Now they gave me an explicit formula. The recursive formula is the other type that I have to write. It says the question. First term 8, get a term by taking the previous one and multiplying it by 2 for any of the other positions. So I can very easily, I hope, identify whether or not it's a geometric sequence by just writing a little bit of the sequence. Don't try and look at the formula if it doesn't fit the way I have it memorized. Just need to make sure. I suspect, for sure, suspect this is geometric because it looks very similar, but it doesn't look exactly like I would want it to look, to just read off everything. So I write a few terms of the sequence and then I know. Now, when they give me a recursive formula, like in number 3, there's not much that they can do to hide geometric formula, geometric sequence formula. Yeah, maybe they put the 3 in front. Still multiplication. It's not much you can do here. Because the recursive formulas are always for us, usually very simple, they can't really mix it up and simplify it to make it confusing. However, I could still, if I want to ask, find the first few terms in the sequence. Start with a 2. It says multiply the previous one by 3, and so on. I already know it's times 3 every time. 3, because that's exactly what the instructions are saying I should do. So this is clearly a geometric sequence. Always say first term 2 and ratio 3. They gave me a recursive formula, so I should find the explicit, the other type of formula, but I have it memorized. 2 times ratio to the n minus 1. So there is definitely a benefit to memorizing this explicit formula, just like I did for, or should do, for the arithmetic sequence explicit formula. Recursive formula, I'm not going to memorize that. It's a translation. It's a direct translation. I would rather understand the language than memorize this. I lose too much. But when it comes to the explicit formula, it's a little less obvious. And I don't want to redo this table every time. It is a little time consuming. It's a brand new sequence that doesn't fit one of my templates that I've seen before. Yeah, the table is often very helpful. It's not a solve all problems technique, but very often it's something I can go to, like we did for the triangular numbers. It wasn't quite an arithmetic sequence, though I suspected it was related. I haven't seen that before. In order to find an explicit formula, I went to the table to help me figure out how to calculate the numbers. Did that, but we did it once, figured out how the explicit formula looks for the geometric sequence, a sequence of this type, and once we did that, we can now use that. I'm not taking a shortcut in my understanding by memorizing this. After I've made sure I understood where this comes from, I can be more time efficient by memorizing. Any thoughts on geometric sequences? It's definitely trying to draw a parallel between what we did for the arithmetic sequences and the questions we're trying to answer here. Type of sequence. Some questions. Now, if we look all the way back to arithmetic sequences. Oh, here we are. If you remember, and I hope you do, mind. Remember, we, after our initial exploration of the formulas, we stepped it up to answer a couple of questions, or a couple of types of questions. Like, here's a sequence, find how many terms there are, or where this last number is positioned. I then identified this one as an arithmetic sequence, which means I know its explicit formula, and I can use that to find the position I'm in here. Just in case people don't. Ideal world, we have a lot of time. We always review everything as it happens. Never fall behind, but it's happened. Right? Let's remember. Exercise 2.2. Now, I won't do the whole thing. I'm just going to set it up to show that what we now have to do is the same basic strategy. And eventually I hit 125. I recognized it as an arithmetic sequence. First term, blah, blah, blah. I therefore had a formula. First term plus n minus 1 times difference. Then I asked, well, let's say this is in position n, this 125. I can name that an and ask in this equation, if I put in the term value, what is the position value? Then we solved it. If this does not ring a bell, you need to go watch those videos. But I assume it does. I'm trying to just remember the strategy because now here in exercise 3.3, we are asking how many terms are there in this sequence? Same kind of question, different kind of sequence. Just write that down. Now, exercise 3.1, 5, 25, 125, and it continues until it hits 9,765,625. That's one thing. The commas confuse you. I'm going to say this, I'm going to do the same thing. What kind of sequence is this? Now it's not arithmetic, it's geometric. I'll write it out, it's new. Geometric with first term 1, ratio 5. Because I've identified it as a geometric sequence, I know its formulas. I can apply those formulas, the templates, to this specific sequence. So I know the explicit formula is an first term times ratio to the power of n minus 1. Positions. Now, I've made it a little bit simpler for us by choosing a 1 here. So this simplifies to just 5 to the n minus 1 because 1 times anything is just 1. Sorry, 1 times anything is that something. However, if I look at the equations that I have from the previous exercise, arithmetic, to this exercise, geometric, it's not the same kind of equation. The unknown that I'm trying to find the value of is this n. Here, the unknown n sits in what I call the base level. Here, the unknown is still n because I'm going to plug in 9765625. Plug in that number just like I did the 120. Ask what is that? The unknown n sits in the exponent level. This is an exponential equation. Obviously, it was just let's call it a normal equation. Different kind of equation, which means solving is going to be drastically different. Luckily for us, we keep things fairly contained in terms of difficulty, so we have some choices. Now I don't know which should I do the easy one. I'll do the easy one first. Choice 1. Choice 2. Choice 1, I can exploit the setting of this question. I know n is a positive integer. Because n corresponds to the position in the sequence, it's not going to just be any number. It can't be a fraction. It can't be anything weird. It's a nice whole number, which means I don't have that many options for what n could possibly be. I'm just going to guess and check my way through this. Because I have more information than this equation is really capturing. I know n isn't just anything. It's a positive integer, which means I have very few options that for which this would work. So now all I'm going to do is I'm going to try some positions, and I'm going to see if I can hit this term 9,000,007 blah blah blah. Because the explicit formula tells me exactly how to calculate it. The explicit formula tells me whatever position you're interested in, plug it in there, calculate the term, and that's what you're going to get. Now I have a target for what I'm trying to get. So I'm going to try position 9. I don't know, my powers are 5, right? Not very big. If I try position 9, then let's use a calculator to find what is the term in that position. Well, it's 1 times 5 to the power of 9 minus 1. So 5 to the power of 8. MathBot says 30625. And now I see, well, I'm trying to get into the millions, close to 10 million. This is a little small. So let's go for 12. Because I'm fairly far away, I'm going to skip some and try position 12. So then I calculate position 12. And now I see, oh, I overshot it. 48. It's too big. So take it one step back and try 11. And there we go. 765, 625 is exactly right. So that's the position. And I can say, I'll do it at the bottom. The given sequence has 11. So there's really, for our level and our purposes within sequences, there's no downside here. This didn't take me very long. I tried 3 times, and I could have gotten away with less. And I found the right position, because there are only a few positions, even in the vicinity of this, because they grow so fast. So there's really no downside for this kind of question to guess and check your way through it. And if you're happy with that, tune out the next few minutes. But if you want to have an alternative and see actually how this is done, feel free to listen for the next couple of minutes. Won't take long. If I don't know where this comes from, and I just have to solve this equation, this is an exponential equation and it's much more difficult. In general, to solve something like a to the x equal to c, so a and c are numbers and x is my unknown, we need what is called the logarithm base a of c, and on your calculator there is a button called ln, which allows me to calculate these as a fraction ln of c, ln of a. Now this is pre-calculus and it's a bigger discussion, so if you're interested, I'm happy to do it, but this isn't really the side note for us. There is a way to find the exponent in the equation. So now Our equation is 5 to the n minus 1 equals 9,765,625. To find the exponent, it's the natural logarithm of 9,765,625 over natural logarithm of 5. Now, luckily, I know what this is already, right? So let's see if MathBot agrees with what we guess and checked last time. Natural logarithm of 976,625 divided by natural logarithm of 5. MathBot says 10. Remember, because we still have n minus 1 is equal to 10, so I have to add 1 on both sides to get n as 11, which we know is correct. We found it here. So this is part of a bigger kind of equation called exponential equations, where if I don't know where this comes from and I just need to solve it, the n could be a fraction, could be any kind of decimal, it could be anything. Then logarithms is how you do it. But we are going to contain this to this kind of sequence where we know it's a positive integer. So we can guess and check and be okay. But again, like with many of these things, we peek ahead behind the curtain, see, ooh, that's complicated. Let's close the curtain. We know it's there, but it's optional to go and explore that further. Any thoughts on this? No thoughts, just stunned silence. All right. To wrap it up by looking at the last kind of question that's similar to what we did in the arithmetic case. Exercise 3.4. Determine the explicit formula for the geometric sequence having 7th term that, 11th term that. They get big. And then I can use the formula, I can answer the 20th term maybe. Very similar to the arithmetic sequence question. So let's take the same initial approach and say in exercise, let's just look at the sequence here. I'm going to have my first term, call it A. I don't know what it is, but in order to really understand the geometric sequence, I need to know that first term eventually. Then I'm going to get the second term, maybe a third. It's there. And eventually it's going to get to the 7th term. And the 7th term is given as 16,384. Then it keeps going. 8th term. And eventually we hit the 11th term. Oh, there's only one in between. Might as well write it down. 11th term. And the 11th term is big. 4194304. And then it keeps going. And in order for me to find other things, I just need the formula. So I know it's a geometric sequence. Therefore, it has a first term and a ratio. So what do we do in the arithmetic case? See how we're building on our experience? We've seen something before. Can we modify it to apply to this new situation? Need to build up with the exercises and the problems. Experience, otherwise much more difficult. Multiply by r, multiply by another r, and another, and another, oops, to get to this 4 million thing. So that means 16,384 times 4 R's will get me to 4. Now I have to solve for R. Well, let's isolate it first by dividing. So R to the power of 4 is 41904 over 16384. Calculating that, final answer, to calculate R from a power, I just take the corresponding root, 6384. See, MathBot, this is your moment. Which is also in any scientific calculator. Sometimes it's a second function, but it is there. 419430 divided by 64, the fourth root. Now, MathBot requires that I type it like this, but your calculator might be. So the ratio is 4. Now I can go to the start and say, well, from A, I have to multiply an R to get to position 2, another R to get to position 3. To get to position 3, I need to multiply by 2 R's. So the number of R's I need to multiply by is 1 less than the position target. Next, to get from A, I have to multiply by 6 R's, and it'll get me to the 7th position, which I have a value for. I also have a value for R, of course. So A is really, nope, A times 4 to the power of 6, because R is equal to 4, 16384. Therefore, the first term is 16384 divided by 4 to the 6. Calculator time. These numbers are bigger. 16388 4 to the power of 6. There's another 4. That's funny. So they're both 4. So I have a geometric sequence with first term 4 and ratio 4. Therefore, I know the formula, explicit formula, of course, only useful one. an 4 times 4 to the n minus 1. If they now want the 20th term, it's a 20. I can calculate that as 4 times 4 to the 20 minus 1. Now, let's see what that is. 4 times 4 to the power of 19. So I need two equal signs, right. Extremely big. Wow. I wouldn't know. These powers increase very, very quickly. 1,0,627,776. Trust the calculator on that one. But the important lesson here is, though the sequence is technically very different from the arithmetic sequence, I've gained some experience when I looked at the arithmetic sequences and their problems. And I can transfer that experience and modify it slightly, but apply it to questions on sequences I've never seen before to build up that experience. If I have a gap in the experience, then this is going to be way more difficult than a progression to learn these things. It's on that. Last, I want to just notice and mention a very, very important application of geometric sequences, where in finance, financial calculations, banks, anything money related, geometric sequence calculations are done literally every hour. It's so common. Let's look at a very simple example to see how these things are related. Suppose you have $2,000 at the end of some year, year one, and I put it in the bank and it pays a well, nice, generous 5% compounded, compounded annually, which means that at the end of the year, they'll add 5%, then that gives me a bigger amount, and next year they'll add 5% of that amount, and so on. No money's added, taken out. Keep it simple. What is the sequence that I how is it related? So, exercise 3.5. We have 2 minutes, we can do it. So, in year one, I have my amount of 2,000. Year two, now when I increase something by 5%, it's 1.05 times the amount. MathBot says I trust you, MathBot. Then I need to increase that. That 2100 is sitting for a year, which means it gets 5%. Now, whether you've done Math 142, we've done percentages and stuff like that. Whether you don't, should be something that we can handle. But let me know if you don't know where this 1.05 comes from. I don't know what this one is. Let's see. 1.05 times 2100. It is 2205. Let's do one more. Then for the next year, that 2205 is sitting there, and that gets interest of 5%, and we get 2315 and 25 cents. Now I don't see a pattern in the amounts, but I can look at the detail in the calculation. This 2100 was 2000 times 1.05. The next one is the 2100, which is this, whoopsie, times another 1.05, so two of them. Next time, I take that 2205, which has detailed calculation, this, and I multiply another 1.05. Therefore, I have three of them. You see, it's exactly the same as the geometric sequence. The sequence of amounts is a geometric sequence with first term 1000 and ratio 5. That's what I multiply every time. So now my formula, I know the formula, is an first term ratio to the n minus 1. And I can find any year that I want. What if they want 10? So year 10, I simply calculate the 10th term. 2000, 1.10 minus 1. That easy. Once I've identified it as a geometric sequence. Let's do it. And I know I would get 3,102 and some cents. So interest rate calculations with this compounding aspect, that is just geometric sequences. And these formulas, of course, in practice, the calculations are a little bit more complicated. You add money, you take money away, all kinds of things happen. But they are still essentially based on geometric sequences. Very practical, very relevant. But like I said at the beginning, we have our introduction. We are peeking at different curtains to see which direction things could go if you wanted to explore that further, but it's not a part of our introduction. This is as far as we're going to go. Next chapter, we'll learn about the Fibonacci sequence. Please pay attention to the schedule. Schedule says tomorrow is a yellow block, which means there is no live session. You video, self-paced, your own time, pause, rewind, do whatever you need. Important. Sometimes it's nice to just do something at your own pace. That chapter, the next chapter, is a little different in terms of the format because these sequences get complicated very quickly. Can't do a lot of calculations with the Fibonacci sequence, but it's very important to know what this is and why it is so important. My apologies for going over the time a little bit. Are there any questions or thoughts or comments, criticisms, complaints, compliments? No? Right, I will see you then when I see you. Look at the schedule, know what's coming up, use your time effectively.